Claudio will talk about the LargeN limit and theta dependence from lattice. Take it away.
Okay, so good evening, everybody. And first of all, let me thank the organizers for giving me this wonderful opportunity. I'm going to present some new results that have been obtained in these works about theta dependence in the LargeN limit in these two theories, the CPN models and the four-dimensional Young-Mills theories. So first of all, let me start with a very brief recap of the main motivations behind my studies. The topological charge, as you know, can be coupled to the QCD action through the dimensionless parameter theta, which at the quantum level introduces a non-trivial dependence in the theory, which is of extreme importance both from the phenomenological and from the theoretical point of view. So in particular, since it enters several different physical contexts, it is interesting to study the theta dependence of the free energy. So this quantity in Euclidean time is defined as minus the logarithm of the partition function, which here is written through the path integral. And usually we parameterize the theta dependence of this function by Taylor expanding it around theta equal to 0. So in particular, chi, which parameterizes the leading order quadratic term, is proportional to the second cumulant of the topological charge distribution and is called the topological susceptibility, while these coefficients, called B2n, instead parameterize the non-quadratic part and are so proportional to higher order cumulants. So the chi and B2n are the main quantities I'm interested in computing. And in particular, I am interested in computing these quantities in the LargeN limit, essentially for their relation with both the phenomenology of theta prime meson and also with theoretical aspects of gauge theories, such as, for example, the U1A anomaly. So the situation up to now is the following. So for S2N gauge theories, using LargeN arguments in the full theory alone, so using just first principles, it is possible only to obtain qualitative behaviors as a function of n of these quantities. And the only exception is the well-known Witten-Vennezian equation, which connects the LargeN limit of chi to the squared mass of theta prime meson. So we need other tools, such as, for example, the lattice, in order to compute these quantities. And up to now, lattice has been able to confirm the leading order LargeN behavior for chi and for B2 within a precision of the order of 5 to 15%. For two-dimensional CPN models, instead, the situation is exactly the opposite so far. Because on the one hand, theta dependence is completely known analytically in the LargeN limit, at least at leading order in the 1/n expansion, and also at next leading order actually for chi. While on the other hand, lattice data so far have failed to confirm these known results. For example, the next leading order coefficient of chi seems to be of opposite sign compared to this prediction. While the leading order coefficient of B2 seems to be larger, of about a factor of 2 compared to the prediction. So in order to clarify the origin of the discrepancy, we would need to simulate larger values of n compared to the ones that can be reached with certain algorithms, which are of the order of 30. However, improvements in this direction are limited by a computational problem known as the critical slowing down, which affects standard algorithms when we approach the continuum limit or the LargeN limit. And the origin of this problem essentially is related to the fact that in the continuum theory, since the charge is bounded to be integer, the topological sectors are separated by infinite free energy barriers, which means that you cannot change the topological charge of a configuration just with a small local deformation of your field configuration. So since standard algorithms generate new values of the topological charge by modifying locally the field configuration, what happens is that as we reduce the spacing, so as we approach the continuum limit, the fluctuations of the topological charge during the Monte Carlo evolutions are more and more suppressed, and eventually the charge becomes completely frozen. So of course it is impossible to compute the cumulants, so chi and the between coefficients. And moreover, this problem worsens as n is increased. As you can see, when we go from n equals 31 to n equals 51, also in this case, the evolution of the topological charge freezes. So the goal of my work has been to improve the LargeN validation of CPN models from the lattice using a new proposed algorithm from Martin Hausenbusch, which is based on a parallel tempering paradigm. So let me briefly explain how this works, and then we go to the physical results. So the idea is that we simulate no more just a single lattice, but a collection of lattice replicas. And each replica has different boundary conditions imposed on a line, which is called the defect. And the boundary conditions on each replica are chosen in order to interpolate between periodic and open boundary conditions. Then each replica evolves independently, but from time to time, configurations of different replicas are exchanged. So the idea of this algorithm is very simple. Essentially, when we are in the open copy, so we give up open periodic boundaries, the charge is no more constrained to be integer, and so it can be continuously deformed by a local deformation of the configuration. So it can be quickly changed in the open replica. So we quickly change the charge in the open replica, and then through the swaps, we transfer the open configuration to the periodic configuration, where the measure of the physical charge, of the integer physical charge, is performed. And as you can see, this algorithm works extremely well, and it outperforms dramatically the performances of the standard algorithm, because as you can see, we are in a very large value, we have a very large value of n, and in a case where the story would be completely frozen, we observe lots of fluctuations. So this largely improves the computation of chi and of the between coefficients. So in particular, we have been able for CPN models to arrive up to n equals 51, as I already said, and we were able to make a best fit of the LargeN behavior of this quantity, n times chi, as a function of 1 over n. And as you can see, in order to describe our data in this range, 1051, we needed up to 1 over n squared terms. And as you can see, with this new data, we observe that our curve approaches the correct prediction for very large values of n. So this means that for the explored values of n, we observe very large corrections to the expected LargeN limits. As you can see, for example, the next to next leading order coefficient is more than 1 order of magnitude larger than the next leading one. So this explains why past works failed to observe an agreement between lattice and analytic results. And this very slow convergence towards the expected LargeN limit is also observed for the quantity n squared b2. As you can see, in the same range, we need to include up to 1 over n cubed terms in order to make a best fit of our data. As you can see, the LargeN limit that we obtain for this quantity is in perfect agreement with the expected analytic computation, but also in this case, you observe very, very large next leading order corrections. Also in this case, this coefficient is much more than 1 order of magnitude larger than this one. So one may wonder why the convergence of the 1 over n expansion is so slow at LargeN for CPN models, unlike, as I will show, what happens for S-H theories. And a possible explanation could reside in the pathological behavior that is expected, at least for chi, in the opposite limit, and when n goes towards 2, which is the smallest possible value. Indeed, semi-classical methods predict that the instanton density di should have a UV divergence for zero-size instantons for n equals 2. So, of course, this leads to a divergence of chi. And besides, in the literature, there were also disagreeing claims about the finiteness of chi. for n equals 3. So it is not clear what happens in this limit for chi. For the B2N coefficients, there is no result in the literature so far. But if we believe this semi-classical prediction, so that small instantons with zero size dominate dynamics, then the simplest guess, by virtue of asymptotic freedom, is that they are weakly interacting. And so we can guess that f of theta for n equals 2 is close to the behavior predicted by the so-called dilute distant gas approximation. So this predicts a dominant cosine of theta behavior, and so that the B2N coefficients are all finite. So in order to test these topics on the lattice, we need to pay attention to a technical detail, because usually when we study an observable on the lattice and we extrapolate the continuum limit, we observe the naive continuum scaling, which is a constant, which is the continuum limit plus order a square corrections. However, we can expect this usual scaling to be modified for small values of n, at least for chi. Indeed, again, using the semi-classical prediction for the instanton density, we can expect that for n equals 3, there is a modification because a linear terms appear, while for n equals 2, we expect from this behavior, of course, a logarithmic divergence, the integral of 1 over rho. Of course, the equation must be taken with a grain of salt because they are perturbative and they have been obtained with a very naive argument. And so they will just be used as a, let's say, a guide to study the continuum scaling at small n. So what we obtain for chi is that for n equals 3, our data point out to a convergent continuum limit with a scaling which is modified compared to the usual one, and in particular, we observe a very good compatibility with a dominant linear correction in the lattice spacing. On the contrary, our data are not compatible with, for example, a logarithmic divergence. So we can conclude that our data for n equals 3 clarify that the continuum limit is finite. Instead, for n equals 2, as you can see, our data are in perfect agreement, both with the dominant logarithmic divergent behavior, which is the solid line, but also with a slowly convergent power law behavior, which is instead the dashed line, which has a dominant small power of the order of 0.1. So it is not possible, although our data are very precise, to distinguish between a logarithmic and a small power behavior. So we came up with a different approach, again based on the semi-classical prediction for the instanton density, which predicts that when n approaches 2, the susceptibility should diverge as 1 over n minus 2. So essentially, we made a best fit of our data for chi versus n, for n greater than 2, of course, using a sort of critical function of this form, which is inspired in form by these ansatz. And we obtain this result for n star, which is the critical value of n for which chi is expected to diverge. Unfortunately, as you can see, this result again supports both scenarios because on the one hand is compatible with 2, but on the other hand, it is technically smaller than 2 in absolute value. So, of course, it technically also supports a finite value, which here is highlighted in cyan. And besides these results having a very large error, it is also compatible with the continuum extrapolation obtained for n equals 2. So again, we can make no clear conclusion, so we have to refine our statistics in this case. For B2 instead, we find that our guess is good because we find that B2 is finite for n equals 3 and 2, and besides we find no evidence of violation of the usual scaling, constant plus order square corrections. However, for n equals 2, we find that B2 is close to the Daiger prediction, minus 1 over 12, but is actually about 3 sigma distant from this value. So again, in order to clarify what happens for small values of n, we performed a best fit of the n small n behavior of B2 And in particular, we looked for the critical value n star such that B2 reaches the Vega value. And we assumed again a critical behavior of this type, which is again inspired by the ansatz for the susceptibility. Unfortunately, also in this case, we find an n star which is compatible with 2 within the error. So we cannot conclude if n star is different from 2 or not. But however, we observed that it is well compatible with the value for which chi diverges. So this leaves open a very interesting scenario in which chi diverges for the value for which B2 reaches the Vega value, which is a Schurian non-trivial fact. Okay, now I would like to show you my results for SVNH theories, because since the Hazen-Bush algorithm has worked so well for CPN models at LargeN, we also implemented it for SVNH theories, because also in this case, simulations suffer from critical slowing down. And as you can see, also in this case, this is n equals SU6, in a case where the fluctuations of the topological charge would be completely frozen, we observe lots of fluctuations. So also in this case, these algorithms has allowed us to improve a lot known results for topological properties at LargeN. As you can see, these are our continuum extrapolations for chi and B2 for n equals 4 and 6. And as you can see, we obtain much more smaller errors on our extrapolation. So this has allowed us to study the LargeN limit of chi and of B2 for SVNH theories. And unlike what happened for CPN models, as already anticipated, we observe a very nice scaling. For example, for chi, we observe a nice constant plus order 1 over n square scaling, as we expect from LargeN arguments. And our LargeN limit...
only a few minutes.
Yes, I'm in time. As you can see from this computation, our LargeN limit for chi is compatible with the expectation from the Witten-Venezian equation. And for B2, instead, in this range, which covers 3, 4, and 6, we observe no correction to the leading order predicted scaling. As you can see, if we fit with a free power, we obtain an exponent, which is compatible with 2. While if we fit with a leading order plus a next leading order term, we find that the next leading order term is compatible with 0. So we can simply describe our data with the leading order 1 over n square terms, so leading to this purely lattice prediction of the value of B bar 2, which improves by about a factor of 3 the previous result in the literature. So I come to my conclusions. So I showed you that adopting the Hazen-Bush algorithm, it is possible to dramatically improve simulations at LargeN, both for CPN models and for SVNH theories. And I showed you that while the LargeN predicted scaling of SVNH theories holds already for n equal or greater than 3, this is not the case for CPN models, where the convergence of the 1 over n series is very, very slow. And this could be related to the critical behavior of CPN models in the small n limit, because, as I showed you, the contribution of small instantons modifies the continuum scaling of chi for small values of n. In particular, we found a finite value for chi for n equals 3, a finite value for B2 for every n, while it is not clear if chi diverges for n equals 2 or not, because the critical value for the divergence of chi is compatible with 2 but smaller than 2. However, we found that it could be possible that chi diverges for the very same critical value of n for which B2 reaches the Vega prediction. So, of course, in the future, I will refine these studies of the critical small n behavior of CPN models to clarify what happens for n equals 2. And, of course, I plan also to extend my studies to other topological observables, such as, for example, chi prime. And besides, I also would like to extend these studies also to non-topological observables of LargeN gauge theories, for example, global masses or K-string tensions, which are, however, affected by the slowing down. So it could be possible to obtain nice improvements adopting the Hazen-Bush algorithm also for these observables. I'm done, and thank you for your attention.
Thank you, Claudio. Now, if there are any questions. Andrea.
Is there any physical consequence you could draw from your numbers? You could get from your numbers or your fits?
So you mean for the CPN models or for the SUN gauge theories?
SUN, because CPN model is kind of
it's just toy model. Well, for Chi-bar, well, we can say that our lattice data fully confirm with a very good precision of the order of 1% the Witten-Venezian equation, because as you can see, our value for the LargeN limit of Chi-bar is in perfect agreement with the one that can be obtained just plugging the experimental values of the square mass of the eta prime meson or of the pion decay constant. So in some sense, our data fully supports the Witten-Veneziano argument to solve the U1A problem. Of course, it would be also interesting to compute, as I already said, the observable chi prime, which is the slope with which the correlator of the topological charge density passes from a certain pi squared to 0, because of course this has to be much smaller than Chi-bar in order for the Witten-Veneziano equation to hold. But this has never been done ever in the literature, because at least from the lattice point of view, and it may be possible for the first time adopting this algorithm that I have developed starting from the Hasenbusch proposal for the CPN models.
All right. Are there any other questions? Ivano Basile.
Yes. Hi, Claudio.
Hi, Ivano.
Long time no see. Ciao. So I was wondering, in your slide number 10, I think I just lost it. You may have said it already, but what's the exponent gamma that you get from the fit?
I'm sorry, I didn't say that, but so the gamma exponent that I obtain is very close to 1. So is about 0.9 and something. I don't remember the exact value, but it is very close to 1, and it is compatible with the 1 within the error. So in some sense, it is close to the
predicted, well, to the guess.
Yeah.
So why do you say that there's no clear evidence for the behavior you wanted?
Now let's say that n star is compatible with 2 within the errors, but at the same time is smaller than 2. Okay.
Oh, I see what you mean.
In absolute value. So I mean, it may be possible that if you reduce enough the errors, you may see a value which is very close to 2, but it is not. It is not 2.
So somehow you still get a finite, if large.
Exactly. The point is that it may be that CPN models have n star very close to 2, but not equal to 2. And so chi is not actually diverging, but it is so close to the divergent point that it is enough to blow up the convergence of the 1/n series for, I mean, n smaller than, say, 100.
Right.
Okay. It would be interesting to perform such a study for example, for SU2, which we know it is finite because SU2 is good. Because in that case, you should see n star very smaller than 2 if you perform.
Sorry, I need to keep the session contained. But
sorry.
Thank you very much.
That's fine. Thanks for the answers. Are there any other questions? Well, if not, I cannot see any other raised hand. So if not, I will thank Claudio for very nice presentation and answer session. And now we will actually, I guess, have to meet